In this section, you will be introduced to another aspect of aerodynamics, the stability of an airplane in flight. Airplanes are designed for many purposes, but most must have a certain degree of stability in order for them to perform their designated roles. By definition, stability is a design characteristic that causes an airplane to return to steady flight after being disturbed. To begin with, let's consider two kinds of stability: static and dynamic. Static stability is the initial tendency displayed by an object after it is disturbed from equilibrium. Let's use a marble to demonstrate static stability. When the marble is resting at the bottom, it is in equilibrium. If it is disturbed, its initial tendency is to return to its original position. This tendency is referred to as positive static stability. When the marble is displaced, in this example, it moves farther away. This demonstrates negative static stability. A marble which remains in its new position after it has been moved is an example of neutral static stability. How an object responds over time as opposed to its initial reaction is called dynamic stability and can be positive, negative, or neutral. An airplane with both positive static and dynamic stability does not immediately return to its original attitude after displacement. Generally, it goes through a series of oscillations, with each one getting smaller. An airplane with positive static stability but negative dynamic stability will initially tend to resist a displacement. Once displaced, however, the oscillations will increase in size, making the airplane difficult to control and possibly leading to eventual structural failure. An airplane with positive static and neutral dynamic stability is also characterized by oscillations. But this time, the oscillations remain the same size and the airplane will not return to its original position. General aviation airplanes are designed to have both positive static and positive dynamic stability. To understand how this is accomplished, we must look at stability in relation to the three axes of flight. First, we will look at stability about the longitudinal axis. This is called lateral stability. Positive lateral stability is the tendency of an airplane to roll back toward a wings level attitude following displacement by a gust of wind or inadvertent control movement. The most common design feature used to attain positive lateral stability is wing dihedral, which is the upward angle of the wings with respect to the horizontal. When an airplane with wing dihedral is displaced in a roll, it will immediately begin to slip in the direction of the lower wing. This creates a higher angle of attack on the low wing, which in turn increases the lift on that wing and tends to roll the airplane back toward wings level. Stability about the yaw axis is referred to as directional stability. When an airplane yaws to the right or left, the large surface area that is behind the center of gravity acts like a big weather vane. This forces the nose of the airplane back toward the original position. The last type is stability about the lateral axis. This is known as longitudinal stability. Longitudinal stability is normally obtained by locating the center of gravity ahead of the center of lift, which is the point along the wing chord where lift is concentrated. This creates a slight nose-heavy condition. To balance this condition, a tail-down or nose-up force is created by installing the horizontal stabilizer with a slight negative angle of attack. If your airplane pitches up because of a gust of wind or momentary control deflection, the horizontal tail surface moves toward a neutral or slightly positive angle of attack. This decreases the tail-down force, and because the nose-heavy condition is no longer balanced, the nose will return back toward the trimmed condition. Similarly, if the airplane pitches nose down, the negative angle of attack and in turn the tail down force increases. This tends to return the airplane toward its trimmed attitude. Additional downward forces are imposed on the horizontal surfaces by the downwash created by the propeller and wings. This means that as you reduce power, the tail-down force decreases, allowing the nose to pitch down. Conversely, when you add power, the tail-down force increases, and the nose tends to pitch up. Although a certain amount of pitch change with an increase or decrease in power is considered desirable, too much change would unnecessarily increase pilot workload. To help compensate for this, aircraft designers frequently raise the engine thrust line slightly above the center of gravity. This creates a nose-down pitching force when power is added, and somewhat offsets the increase in tail-down force caused by additional downwash. Since pitch stability depends upon the difference in location between the center of gravity and the center of lift, the CG's location obviously plays an important role in how an airplane handles. By paying close attention to where and how much fuel, cargo, and people you load on an airplane, you can ensure that the center of gravity will remain within the limits set by the manufacturer. If too much weight is loaded in the front section of the airplane, the CG will be forward of the limit, making the airplane nose heavy. If this happens, there may not be enough elevator or stabilator force available to rotate the airplane for takeoff, or to raise the nose of the airplane during the landing flare. A much worse situation occurs when an airplane is loaded with the CG aft of the approved range. In this case, the airplane will be very unstable in pitch. Even with full forward pressure on the control wheel, recovery from a stall might not be possible.
Although it's possible to learn the mechanics of flying without understanding aerodynamics, a basic knowledge of how an airplane flies and why you must take certain actions will make you a more competent and safer pilot.